All right, main objective today, we are adding, subtracting, multiplying, dividing our functions, and we're also going to compose them, find the composition between the two. Okay, so let's start with the four main operations. And this first slide here, this is really just about notation more than anything. Okay, so if you were asked to find f plus g of x, please understand that that's the same as saying f of x added with g of x. Okay, so it's like I can separate the two functions, evaluate each of them with x, and then take those two results, add them together. Okay, and it's very similar for the other three operations you see there as well. All right. Now, the one you got to watch out for is your quotient or division between f and g. So f divided by g of x, that's the same as f of x divided by g of x. You're creating a fraction there, right? If g of x has a variable to it, you have to be mindful of any values that would make that denominator turn out to be 0. So that's one thing you got to be careful about. Okay? The domain for sum, difference, and product is always going to be the overlap of the two functions' domains, whatever they have in common. The domain for the quotient is going to be the same thing, except you might have to exclude a value or two that also makes that denominator g of x equal to 0. Okay? So let's look at some examples to support this. All right, find f minus g of x if f is x plus 1 and g of x is x squared minus 1. So by the notation there, this is the same as saying f of x minus g of x. F of x is x plus 1. G of x is x squared minus 1. Notice my use of parentheses here, very important, because that shows I'm supposed to distribute this negative into g of x. That's going to give me x plus 1 minus x squared plus 1. And, of course, I got some like terms there that can combine. Here's my result. Okay. All right, next we want the product of f and g. That's f of x times g of x. And this is nothing more than distribution, or FOIL as we like to call it. You'd get an x cubed first, a negative x, a positive x squared, and a negative 1. Now, I'm okay if you leave it like that, but it is pretty customary to reorder your terms in descending power. Okay. All right, now let's pause there and come up with the domains of each of these. Previous slide said domain of sum, difference, and product is the overlap of the domains from the two originals. Okay, well, this is really easy. F is linear. What's the domain for any linear function? All reals, right? This is got a domain of all reals. And g of x is quadratic. That's a parabola if you were to graph it. What's its domain? All reals as well. Okay, so clearly the overlap of those two is all reals. So I'm going to say both of these have a domain of that also. All right, now, quotient, you've got to be careful here. This is the same as f of x divided by g of x, or x plus 1 divided by x squared minus 1. Is that simplified?
No.
What can I do to simplify it?
You can factor out the x squared minus 1 into it.
Very good. So I'm going to factor the difference of squares. And what's that allow me to do? Oh, he said it. He said cancel. Bad verbiage. Okay. What's the result of canceling? When you cancel two things, the result is always 0. These aren't resulting in a 0 when I cross them out. They're both technically resulting in 1s, right? So I'd say a common word that we misuse here is the word cancel. Try to say reduce instead, okay? So we're going to say those reduce away, and what we're left with is 1 over x minus 1. Okay, and that is simplified. All right, now, domain is got to consider the fact that we have a fraction here with some variables in the denominator, right? What is x not allowed to be? Okay, x cannot be 1. And you probably answered that from the final denominator here. But we have to answer domain based off of the original denominator before we simplified. So include -1 as not being part of the domain as well. Okay, so we're really looking at this line or even this line right here before we reduced and saying there's 2 excluded values. Okay. All right, so you could write it like that, or you could give your interval notation. Like so. Questions there? All right, example 2. All right, so here we are given the graphs of 2 different functions. F of x is the red graph. G of x is the blue graph. Notice they are both functions. They pass the vertical line test. And first we're asked for f plus g of 2. So this is just understanding the notation that this is the same as f of 2 added with g of 2. All right, if you look at the graph, f of 2, well, when x is 2, that places me right here on that graph where the y is 2, right? And then g of 2, when x is 2, I'm right here where y is 1. So altogether, f plus g of 2 would equal 3. Okay, very similar approach for the next one. This is f of -1 minus g of -1. Well, f of -1 appears to be 1 minus g of -1 appears to be 2. So my result is -1. Next, we have f plus f of 0. That's f of 0 plus f of 0. All right, well, f of 0 places you right here. When x is 0, y appears to be 2. So this is going to be 2 plus 2, or 4. And lastly, f times g of 2. That's f of 2 times g of 2. Well, we already found f of 2 in the first problem. That's 2. G of 2 we said was 1. So 2 times 1 is, of course, 2. Okay, now I'd like to find a graph to represent all of f plus g of x. Okay, so take some critical values here from the 2 functions. So starting on the left side here, when x is -4, we have f of -4 would be 1, and g of negative 4 would be negative 1. So if I add those two together, what's the result? 0. So I'm going to have a point right here on this new graph. Okay. When x is negative 3, f of negative 3 is negative 1, and g of negative 3 is 0. Adding those two together, you get a negative 1. When x is negative 2, f of negative 2 is 0. G of negative 2 is 1. Adding those together, you get a 1. At x equals negative 1, f of negative 1 is 1. G of negative 1 is 2. 1 plus 2, 3. When x is 0, f of 0 is 2. G of 0 is 3. 2 plus 3 takes me all the way up to 5. When x is 1, f is at 3. G is at 2. 3 plus 2 is another 5. When x is 2, f of 2 is 2. G of 2 is 1. Those are going to add to a 3. And that is what we actually found right here. That's that very first problem, right? F plus g of 2, we said, is 3. Okay, and then the last final value I'm able to plug in would be when x is 3. Okay, f of 3 is 1. G of 3 is 0. Those are going to add to a 1. Okay, and then I can just connect here. Now up at the top, you're going to have a horizontal segment there. That's just verified. Like if you look at when x is 1/2, both f and g are 2.5, right? So 2.5 plus 2.5 would put you at 5 as well. Okay, what's the domain of that guy? Negative 4 to 3. Non-inclusive or inclusive? Inclusive for both. Very good. Okay, now compare that domain to the domain of the two original graphs. Okay, the blue graph has a domain of negative 4 to positive 4, and the red graph has a domain of negative 4 to positive 3. So if I take the overlap of those two, that gives me the domain of the sum, which is negative 4 to 3. Okay? All right, moving forward. Example 3. Here you've got f of x again in red. I want to find y equals f of x plus 2. I want to graph it. Okay? Again, this is just about understanding notation. F of x is a fancy way of saying what? Y. So all this wants me to do is take the y values of the original function f and add another 2 to them. All right? So if I start here on the left side, when x is negative 4, I have a y value initially of 1. I'm just going to add 2 to that, and that's going to move me up to a 3. When x is negative 3, y initially for f is at negative 1. Adding 2 to that, I move up to 1. Okay. When x is negative 2, on f, y appears to be at 0. I'm going to add 2 to that. Moves me up to 2. And then you get the idea. Every point is shifting 2 units up. Okay. So this is what we call a vertical translation, right? The graph looks the same as the original function. It's just been shifted upward. Okay, so then by the same reasoning, if I want to graph y equals f of x minus 2, I'm going to take the red curve and I'm going to subtract 2 from each point's y value to translate it 2 units down. we are. Okay, don't overcomplicate that. You add a constant to the end of a function, it's always going to give you a vertical translation. All right, example 4. What's next? Now we're going to talk about compositions. Given two functions f and g, the composite function is defined as follows. Two notations that represent the same thing. Okay? This first notation, you have this open circle between the f and the g. We would read that as composed. This is f composed of g of x. F composed of g of x. Or the other notation that means the same thing is f of g of x. This is an operation specific to functions. Okay, so you can add, subtract, multiply, divide real numbers. You can do that with functions, as we've seen already. Compositions can only be done with functions. You can't do a composition between real numbers. Okay? It says the domain of the composition is the set of all of numbers x in the domain of G, such that the range of G is in the domain of F. That's kind of tricky. Basically, what that statement is saying is that the range values from the inner function, so the inner function in this case I would call g of x, whatever those output range values are, they turn into the input domain values of the outer function. They go from being y values on the inner function to being x values on the outer function. Okay? All right, so some examples. Here f is quadratic, g is linear. First thing I'm asked for is f of g of 3, or f composed of g of 3. So that's the same as saying this. Start on the inside. Find g of 3 first. So g of 3 simply means to take 3 and add it to 2, right? That's going to give me 5. All right, now understand that 5 by itself is a range value for the function g, right? I plugged 3 in for x, I got a 5 out. But now what I'm going to do is treat that 5 like a domain value for the function f. Okay, that's the whole idea of a composition. So what's f of 5? Well, that would be 5 squared minus 3 times 5, 25 minus 15, or 10. All right, next we are asked for g composed of f of negative 2. So that's g of f evaluated at negative 2. So I start by plugging negative 2 into the function f. That's going to look like negative 2 squared minus 3 times negative 2. Okay, so that's 4 plus 6, or 10. That 10 is considered a range value for the function f, and I'm now evaluating function g with it. So the 10 is turning into an input domain value. 10 plus 2 then produces a 12. All right, and then lastly, what's f composed of g of x? Here, I'm trying to create a formula or an equation that can be used to find all values for f composed of g. Okay, so this is f of g of x. Now, g of x equals x plus 2, right? I think x plus 2 is the formula that represents your y value for that function. What I'm doing is I'm evaluating the other function f with that y value of x plus 2. And don't overcomplicate it. That means take this, you're plugging it in here, and you're plugging it in here, right? X plus 2 squared minus 3 times x plus 2. Okay, that's going to give you a trinomial, x squared plus 4x plus 4. Then we distribute minus 3x minus 6. Combine your like terms. X squared plus x minus 2 is our final result. Now, I can check if this appears to be valid by going back to the first problem. F composed of g of 3 gave me 10, right? So if I plug 3 in for the x's here of this result in green, I better get a 10 as well. 3 squared is 9, plus another 3 is 12. 12 minus 2, 10. Matches over here. Okay. I could not use this result to check what's in red here in the middle because this is G composed of F, not F composed of G, right? Questions on any of those three examples? All right, next we have two more functions and we want to find the composition as well as its domain now. All right, so f of g of x is f evaluated at the square root of x minus 3, right? We're taking this square root function and we're plugging it in right there is what this wants me to do. That's going to give me 1 over the square root of x minus 3. Is that simplified? Why not? Yeah, we don't like radicals in the denominator, right? Because square roots are potentially irrational, aren't they? If it's not of a perfect square. And we don't like dividing by irrational numbers. So we need to rationalize the denominator. How do we do that? Mm-hmm.
Square it.
Can't square it. Not quite. I do need to multiply, but not by an inverse. Parker?
Multiply both sides by x minus 3.
When you say both sides?
Like the numerator and denominator.
Okay. So you want to multiply both sides by x minus 3?
Yeah.
Like this?
Yeah. I thought you did it by the square root.
Yeah, it's got to be the square root of x minus 3. Okay? All right, now going back, somebody had suggested squaring first. Well, I can't square because this is not an equation. I can't use an operation here because I can't do it to the other side. All right. What does this red fraction equal? 1. When you multiply something by 1, it doesn't change its value, right? What I'm doing here is I'm just manipulating this original fraction to look a different way. But it's still going to be the same value. It's still going to represent the same set of values, okay? My calculus professor in college, he called this, he would refer to these as clever forms of 1. Clever forms of 1, okay? Now, what that's going to do is give me the square root of x minus 3 up top. And then down below, it's going to give me just x minus 3. Square root of x minus 3 times itself, the radical wipes out, right? So this is simplified now. Okay, now to find the domain of this composition, notice what it says here. First begin by finding the domain of the inner function. The inner function in this case is g of x, right? Okay, so what is the domain of that? No. Not all reals. It's a square root function, right? So that radicand can't be negative. X has to be greater than or equal to 3 there, yeah? Once you come up with the domain of that inner function, determine are there any values from that that cannot be used in this result that we got for the composition? Are there any values that are 3 or greater that I cannot plug into this fraction and get a result? 3 itself, right? It's going to make the denominator 0. So I'm going to have to say the domain for the overall composition is simply x is greater than 3, not greater than or equal to. Make yourself a note. It's really subtle if you go back and look at these to miss why we're no longer including the 3. We'll say must exclude 3 because it would make the denominator of f of g of x 0, equal to 0. Okay. So you can give that, or of course we can do interval notation 3 to infinity. Questions?